another special interest group focused event. This is a few hours together this morning. You've all gathered here because it sparked your curiosity, I'm sure, and really want to maybe unpack a little bit of the topic that we picked up on. So if I just click here, it should go forward. Sorry, do I need to do presentation?
Yeah.
Cool. Great. Okay.
Yeah, okay.
So, hey, of course, we always look for good feedback. Sorry, feedback. Feedback from our attendees on the virtual attendees, but also obviously you in person here. So, feedback, like, it always allows us to really absorb it, good or bad, and then allows us to refine the next event that we do. So just to, again, sorry, am I clicking the wrong button here? Oh, it's that, okay. Okay, so thanks, Lena, for the introduction. Yeah, we're acting as the host today. You're in this environment. You're in the Silverstone Technology Cluster environment as well. And really, for us, I'll hopefully steer the day. I'll be doing handing over to some of the interesting speakers that we've got lined up, but also we'll have a Q&A session at the end. So what I'm really anticipating is that there's going to be loads of good questions. I'm not an expert in everything we do, but there'll be certainly experts around in the room. So again, this is just to re-emphasize, this is a special interest group, and I think a lot of you have recognized some of the faces. I've been to these events before, and we have lots of events, and we have some more events planned for this year as well. So it's always an opportunity in the space that we're in, and there's a small group of us in the cluster group that have identified areas that we can talk about and we are specialists in. And this particular interest group is design engineering and metrology. That is quite broad in its wider sense, in that it's a full workflow really from all design concepts in a virtual world, but also into the metrology, which could be a combination of virtual and the physical world. And if you look around here today, you'll see some of these physical objects that are validating parts and components that are around. So as I say, I've left I always like to go to a dictionary because I always have to remind myself what artificial intelligence really is, because we hear a lot about it, obviously. So, yes, if I pick whoops. Sorry, IT. Should that be moving?
Yes, it should be.
Override it. Right, fine. So let me just spend a minute just re-emphasising, why, as Hexagon, we've been here as a founding member of the Silverstone Technology Cluster, and we've really enjoyed that period and that journey with them. But it's important, I think, when you look at it, is to sometimes question, well, what's the purpose of it? Why are we here? Why are you here? Why have you got that cluster group that's grown so significantly now? And there is a core objective, of course there is, and it's all about supporting growth and the growth and the support. We recognise that within a cluster, within the environment we're in the UK, the companies, entrepreneurs, people that are starting up, got new ideas, new innovation. They haven't got all the tools in the tool bag. So they really want to be able to tap into tools. They want to be able to look and see both in a mix of services, how they can get their business starting up or from A to B. What is it about? What is it they need from that? So there's the nice thing about the Silverstone, the STC, is that we've carefully guided it so that we have a nice mix of service consultants, providers, but also technology. So that's always a really careful balance that we keep forward. because ultimately in a business, if you're starting up, you need all of it anyway. So that picture I've got there is, there's I use it to describe it, is that we're here and we're providing all the ingredients. It's down to all of our members to be able to step forward and say, do you know what, I want to be making a cake, so I'm going to have to go and get the ingredients. It's not about us being too imposing. We just need to build that support structure around us. Okay, so there's about a little bit of passion around the SDC. So now I get an opportunity just for a little while, just as the host, just to give you an update and just to let you make you aware of Hexagon itself. Again, most of you probably know us, but always good for me to give you an opportunity. We've got, because we changed quite a lot. We're evolving quite a lot as a company. We're now up at 3.8 billion in 2022. It's actually over 4 billion. 4 billion business globally, covering all of the regions and the whole footprint of the globe. And here are some of the things. We're focused on autonomy, very much got a thread and link to today, innovation, and we're driven by purpose. So those are some of the headlines. I won't go into too much detail there. I won't consume the day. So again, what we're recognizing as a group, as a total group within Hexagon globally, is these are the challenges in the fast changing world. And of course I highlight there, one of them is in artificial intelligence, the focus for this session this morning. For all these others, you've all heard about them, and they're a mix of humanities and technology and challenges that we have as a total group. It must recognise your hand, I think.
There was a bit
It's just me.
So apologies, because we're having a bit of a technical glitch at the moment. There we go. And now.
There we go. Cool. Again, shall I go through that lot? With the size of the business that we are, and by the nature of what we do, we're pretty well touching anybody in the world that is making anything. And that's through all sectors, segments, and you can see we tend to slice it up into the verticals, which are all the big ones there, as you see. And some of the names, I'm sure you'll recognise a lot of those inside that space. There's a real good video that's 2 minutes, and then I should hand over to the first speaker, but it takes you on a whirlwind, quick journey through Hexagon and what we do. There's an even shorter video, which is everything Hexagon don't do. So that's pretty quick, pretty brief. So look, let's get on to the main topics here. So thank you for that a few minutes of opportunity just to fly the flag for Hexagon a little bit. So here we go, and in a minute I'm going to hand over to the first speaker today. Really interesting topic, I'm sure. I think the neuro bit has caught my attention straight away. So I shall be handing over to Andy Fine in a while just to go on to his presentation. You know, AI, A Brave New World is the title of today. And is it really a new world? No, the brave bit, I think, is the bit I focus on. Because it's not a new world. AI has been around for a while. We even when we came into work this morning, I'm sure it have been there around us. It's already been applied. I think that the brave bit is about really being able to take a view, go and have a look at where the technologies and where they are now and how they're advancing, because they are going at an incredible pace. Where AI now our life will get easier. As humans, it's all about getting life easier, and for business, it's about getting it more efficient for me. So hopefully you'll get a really good, interesting few hours now of a real bit of a deep dive into some specific applications. Okay, so with that, if I can hand over to Andy. Oh, sorry, Andy, you're right there.
Yeah, I'm trying best.
Will this naturally follow straight on?
Right, there we go. Thank you.
Thank you.
Thank you very much. Right, good morning. So I'm Andy Fine, so I'm the commercial head for Neural Concept, which is a relatively young company. We're only 3 years old as a company. We're a spin out of EPFL in Switzerland, which is, see why you can see there's a Switch watch sponsorship on one of the, I'd say, the more fun projects that we're involved in at the moment. So I'm going to go into this one a little bit later, but this is a team in Lyon in Switzerland that's trying to break the world sailing speed record, which is something that's a little bit crazy. They're trying to do hitting nearly 100 miles an hour sailing on the water, which I think the pilot's probably a little bit braver than me. I'll go into this one a little bit later and some particular challenges in what they're doing, but let's say if you're interested in anything marine, anything such as that, really fascinating what they are doing. Okay, so I took the title of today's presentation, A Brave New Dawn, and I thought, oh, okay, well, what does that mean? It's a brave new dawn. We all know the answer. The answer is AI. But what's the question? And I think most people in here will know the meaning of this, that we all know the answer, but we need a much bigger computer and a much more explanation to find the question. So what is the new dawn? And it's really, how many new dawns are there? How many different types of AI are there? And we'll go into it a little bit as I go through today. So our version of AI, we're calling engineering intelligence. So what is exactly engineering intelligence and why do we need it? One of the main aspects we need to cover, and I think this is particularly resonating with clients that I've already spoken to and some of our customers, is retention of knowledge. So when I speak to customers, whether this be aerospace customers that I've known and have been customers and friends of mine for a number of years, or certain automotive customers, one of their biggest issues is loss of knowledge. So they've got engineers who've got this massive wealth of experience. They've been designing cars, planes for 30, 40 years. Now, this entire generation of engineers is retiring. And I know a few engineers, particularly who I've spoken to, who said they're not retiring yet because the knowledge hasn't gone to the next generations. And how do they get that knowledge? And they're really searching, okay, how on earth can we get this knowledge and retain all this data? This is one thing that we can actually answer with engineering intelligence, which is a really nice thing to be able to do. The other two parts are things that have been talked about in the simulation industry for a very, very long time. So better performance, so cheaper, faster, better. This is something I've probably done since I started in the CAE industry nearly 20 years ago. and shorter design cycles. Everybody needs shorter design cycles, wants to get things out quicker. This is almost even more pertinent in the automotive industry at the moment, where everybody's basically scrapped everything that they've been doing for the past 50, 60 plus years in IC engines, and everybody's going to EVs and so on, and it's a completely new product range for most people. Now, this is also true in the aerospace market, where everything needs to be completely new, building from the ground up, and the design cycles are much shorter. None of these companies are getting more engineers and more people to do it, so they've got to do more in less time. So we need to build some tools to do this. Now, I want to be very clear at the beginning here. I'm an evangelist for simulation. I love simulation. I've built my entire career on simulation. I think it's really the best way forward. And I think actually simulation can start taking the place of a lot of experimentation now, because I think simulation's got that good. It's also going to give you much more insight to what's happening inside something. You can't open up a box and see everything that's happening inside a box on an experiment. You can do it in a simulation, so it's really powerful. But we're reaching some limits. So speed limits. Are we plateauing in how quickly we can get our simulations out? Moore's law would only go so far, and now we're going to GPUs, so there's some more acceleration, but we're hitting some speed limits. There's a scaling cost of things. Everybody's using HPC, something such as that, but we know HPC costs are getting higher and higher. You just look at how much, which is publicly available, say the Formula One's companies spend on their HPC clusters every couple of years, and it's absolutely enormous figures. So the scaling cost, it's not for everybody. Not everybody's got 7-figure budgets to scale the simulation. And then automation. Okay, automation, most people are doing it. There's a lot of companies offering services to automate the simulation, but it's not always that robust. So it breaks. And when it breaks, you need specialists to fix it and so on. So we need something to kind of override all of this. So what's the solution? So we had a little bit of a think about this, and we came up with something that we call software 1.0. Our software 1.0, this is what we've seen in the past 10, 20 years. So simulation software, basically doing everything. Eating the world, replacing some experiments, really coming to the forefront that most engineering companies are using simulation. Now, what do we see as engineering intelligence? We see that as software 2.0, where engineering intelligence, neural concept, we're eating all of that software, all of that data. So all of the simulation data, and I can go into a little bit later, actually all the experimentation data as well. So from neural concept, anything that has a 3D representation, so a 3D geometry, whether that's a real thing or a virtual thing, and have physics associated with it. So it doesn't matter whether it's CFD, structural, explicit, EMAG, whatever it may be. We can read all of that and then generate this wonderful neural network for what we're doing. So I think I've set the setup for what we're doing. It's probably about time I explain what we actually do. So let's go into the technology. So technology behind it is a form of AI. Now, AI is an absolutely huge field. Now, you think AI, it's even bigger than CAE. And you can say, right, we're going to apply AI. What on earth does that mean? So you look at just a few of the things where AI is involved. So we know AI is in protein folding, molecular discovery, so a lot in the medical industry, the 3D reconstruction we see, the autonomous driving, the apps that we use. So anybody who travels all over the place, when you've got your phone and you're looking at a menu in a foreign language, just hover over it, translates it. It's another form of AI, and particularly AI deep learning. So deep learning, formation of neural networks. I'm not going to go into the real nitty-gritty technical detail, because I don't think it's necessary here, but this is the field of AI that we're looking at, and the field of AI we're looking at here. So what's the technology we do? So it's a form of AI called deep learning, or 3D convolutional neural networks, which I know is an absolute mouthful. But effectively what it means, it will take the learning from any simulation or experimental data you have. So think of it as an engineer, and think of it as actually an engineer that you're training. And you're giving that engineer all of these different simulation examples, you're giving it all the physics examples, you're showing the engineer all of the different experimentation you're doing, and that engineer's learning what happens when you put different shapes, different loads on things. In this example, we've just got I think this is just a marine propeller. But here, you can see examples here, we've got from 4 blades going up to 7 blades in this case, and different shapes and different forms and so on. Now, you imagine an engineer in any field, an engineer, say an automotive engineer, they've seen vehicles being developed for the past 10 years, they've seen a lot of different vehicles come. They're going to know as soon as they see something how it's going to behave. Is it going to crash in the right way? Is it going to be aerodynamically efficient? Is it going to have the aerodynamics of a brick? That engineer will know. And what our AI, our neural network, is doing is exactly the same thing, but much, much quicker. So the more data you can feed it, the quicker it can learn. Now, in this case, let's say it's learned from a whole different range of propeller designs. And then what it's come up with is the ability to predict the performance of a new design without ever seeing that design before. So it's taken all the things it's learned from all the different trainings it's had and said, okay, I've seen this feature on this model, I've seen this feature on this model, this feature on this model. And then it's used the neural network to have an accurate prediction of the quantities of interest. And I say, it doesn't matter what the physics is. So it's purely a relationship between physics and shape. So let's give an example. What does this actually look like? So we said we need to go to shorter design cycles. We need to go to, I think you're going to probably hear the democratization of things a lot, and you're probably hearing that a lot already. So this is an example. This is an integration with ParaView. It's not supposed to look quite like that, but it's something on the IT side, but just of a Formula One wing. What you're going to notice here is that new geometries are getting uploaded and the prediction is instantaneous. It's like the results are already there for whatever new geometry you have. So here, uploading a new geometry file, clicking predictions like that. It's literally milliseconds once you've got the neural network up and running. And this is key in the democratization and the shorter design cycles, because you no longer need to be a simulation expert to get the results out of something. And that's pretty huge. So I think a lot of people have tried to do upfront simulation, but when you don't have to do simulation at all, you can just focus on the physics and the quantities you're interested in. I mean, that's incredibly powerful. This is the kind of thing we're doing here. That's not to say, and I want to bring back the caveat, this isn't going to replace simulation. This isn't going to replace simulation engineers. This is enabling the simulation engineers to do much higher fidelity simulations, and you need those simulation engineers, those analysts, to train these models. But these models can then be used by your designers, people up front who don't need to have, who can just focus on my favorite subject, which is the physics. This is another example. So this is the satellite panel from ESA. This is an integration with Onshape. But this is really just to show you that technology can be integrated into pretty much any program you want. So whether it's Onshape, a CAD platform, and so on, all of it can just have an API that goes into the simulation. Neural network can be read from anywhere. You can do it on a completely independent app as well. So it's pretty flexible how it works. So this is really just going in more into what I previously said. So this is the traditional workflow of software 1.0. So design team designs something, asks for simulation, simulation comes back, sometimes in a few minutes, sometimes in a few hours, sometimes in a few days, sometimes in a few weeks, if you're a crash person. But how can we improve that? You can see we've still got the simulation engineers, we've still got the analysts, but they're doing much higher end work now. They're not, there's no compromises in the simulations they're doing. They're not compromising for time, they're not compromising for the HPC they've got available and so on. They're doing really high fidelity stuff. Training the model and then the simulation is done in the neural network. The designs are optimized by the designers, and then by the time it comes to what we call a kind of semi-optimized design, and goes back to the analyst, they're basically doing what you'd think of as a virtual prototype. There's a pure digital twin, all the prototyping is done virtually, and the aim of this is that you're going to get to your final product much quicker, and a higher end product as well. So how does this differ from traditional machine learning and what we've done for years and years and years? So I remember a very long time ago, so this was probably in the early 2000s, talking to clients about optimization. And I won't mention who I was working for back then, but it was to say, actually when I was an engineer, so it was pre my commercial days, and we were talking about optimization, and really most machine learning has stayed on the left hand side of this than traditional machine learning. Now, where you have a specialized model generated for each program. That's still going on today. You look at a lot of machine learning codes, you look at a lot of actual codes that call themselves AI, they're still in that project early space. What we're doing here is to create one general surrogate or one general pre-trained model for your environment that can be used across programs. We've had great examples from clients who say have three or four different programs of development, or three or four different product families. We've learned data on all of those different product families and used our neural network to actually create something new that's a combination of all of those different products that optimizes all of it. So this is perfect when you talk about e-motors, for example. But this can go even further. So say you want a general neural network model for aerodynamics. Now, okay, we can do aerodynamics and we'll just learn all of the Formula One car and just do a Formula One car. But what if we took all the engineering and aerodynamic data that a company has? So a company, I don't know, and I'm saying this is a pure caveat, this is not real, but a company such as Ford, who make everything from sports cars to pickup trucks to vans and everything. What if we were to learn several thousand of their aerodynamic data? So this is all their vans, so both the wind tunnel experiment and the simulation environment. We could create a general surrogate model that will predict everything on their new product. It will see almost every aerodynamic feature that could exist, probably does exist in this massive product range. And the neural network can be intelligent enough to have a good prediction on all of these quantities for any new design that comes forward. This is really where we can get to. I can get really visionary in the future and say, well, how can this really change the world? And this is what certainly our CEO is really interested in. How can we change the world and make the world a better place? Now, I want you to imagine something. Now, imagine when you're going to your doctors and you have to have some kind of surgery plan, something such as that, whether it's a stem model, something such as that. Now, imagine the doctor could take a CT scan of your body and plan a surgery instantly on his computer, say, right, I'm going to put a stent in. How is that going to change the blood flow? How is that going to heal you? And the AI model can instantaneously predict that, yes, this will work, or you need to try something else. This is what this technology in theory is going to be able to do in a few years' time. We're not there yet, but that's the ultimate vision. And this is where we think, actually, we really can be world-changing in what we're doing. Going back to the automotive side and back to what we're doing now, this is realistic for what is happening now in the engineering sense, but we're already working with some biomed companies who I'm not able to mention. But if I look at our long-term impact on things, company I am able to mention that we're working with is Airbus. And I think everybody in this room knows that Airbus's design cycles and so on are several years long. But Airbus is already a client of ours, and we're going to be heavily involved in future projects for Airbus. So let's have a few different applications, and you're going to be the first audience to see publicly this application, because it's literally just been approved for distribution. So this model here is for a phone manufacturer. So you take your phone, you drop it. Well, everybody drops their phones. We all do it all the time, but we all hope that they still work. And we'd be annoyed if we picked them up and they didn't work anymore. So what do all these phone companies do? This doesn't matter whether it's Apple, Samsung, whoever it may be. They do lots of drop tests at different angles and so on, and they've got different PCB layouts in the phone, and they have to simulate all of this to make sure the components don't fall off and so on. So you look at the componentry, please work, there we go. And you can see this is the typical explicit analysis of a drop test on a corner of PCB. Now, how many designs can you reasonably explore in the time? So if you do it manually, you've got to move the chips, move the bits manually. How many times realistically can you go through that to explore different designs? And when you have a new design, how many different tests can you do? And this is kind of a real question there. So what we did here, we took numerous, it's working wonderfully. We took numerous explicit tests of this drop test. And now I have to be very clear, we didn't cheat, we didn't do this one. So the way we do it, if we've got, say, 1,000 samples or even 100 samples of data, we'd only train on, say, 80 of them. And that other 20 we use for testing and validation to make sure the neural network's actually telling us the truth. Because what's the point in testing a neural network on something it's already seen? You're not really testing the network on what it can do. So we don't cheat. And when we're validating, we're looking at how the neural network's performing. You can see we're coming up with examples such as this. And you can see that actually from the explicit, from the actual simulation, which I see the simulations are as good as experimental data these days. I think simulation technology is so good these days that you can count on that. And when you look at what we call the shape prediction, which is our neural network model, they're pretty much identical. And from my experience in the world of AI and simulation, neural concept is the first technology that I've ever seen. From my knowledge, we're the only technology that can actually do this purely based on shape. And I'll be very clear, there are 0 parameters here. No parameters whatsoever. This is just based on the shape and what we're doing. So the technology here, when I first saw this, when I first started talking to the company, I was absolutely amazed, and I thought we've hit the holy grail here. And that's probably why in a company that's as young as we are, we've got companies like Airbus, and we've got some very significant blue chip companies that we can count on our client list. I wish I was allowed to tell you all the blue chip companies, but they make us sign NDAs, which if I told you, we wouldn't be a company anymore. So Airbus, this is something I mentioned a little bit earlier. Here we're looking at transonic CFD, so anybody who's a fluids person will understand this is not the simplest of things, but already having great success and predictions, and this is currently in use by Airbus research at the moment. I apologize, I know I'm probably talking far too much. Another example, again, this was done with Numica. This is Numica before they became part of Cadence, but in turbo machinery, and another company that we're allowed to talk about is Safran, who we are very lucky to count as a client, as a partner. And what you're actually seeing here on the right is a typical example of our online app. So this is just simple uploading of new data, instantaneous predictions. Now you may think, okay, I can do these predictions. What about optimization? And I'll be honest with you, optimization is in there. You can do the optimization, but we're not focusing on that at the moment because we don't want to be lost in the whole optimization world, as it were. Another example, and this is probably the last, I'd say, serious example from me, is something, again, that was released at the beginning of this year, and this is crash simulation for battery housing. So Mobia is a tier 1 supplier for the automotive industry, and they wanted to start using surrogate models for multiple physics. So they're doing cold plates with us as well, thermal side, but they let us actually release the data for their crash simulations to actually look at, okay, what is the achievement we've done? So can we predict their crash simulations, the output of their crash simulations with the neural network model in milliseconds? Yes, we can. And say the chap down here, Nicholas Klinke, who's the team leader for that, he's presenting at various conferences in Germany at the moment. He told us that they had probably something over 90% saving in time from starting to implement this technology. So it's allowed them to move much, much quicker. And they like pretty much every company I know at the moment, is really struggling to recruit and start struggling to find the people. So being able to do more with less is really what they want to do. I want to finish with the last couple of things that are a little bit more fun. We like doing world record, and we like doing fun stuff as well. So this was one example we did of a world record design. So that is actually a bike under there, in there, and that bike broke the cycling world record. So this isn't the Guy Martin going behind a van on a bike. So this is actually involves some aerodynamics. But this bike set the world record for both male and female cycling. Now, if you can imagine cycling at 80, 90 miles an hour, that's in a little box like that. It's a little bit scary, but these, this is why students did it.
Still an order.
Exactly. But they used, I think they had about 100 and something CFD simulations, and then they used the neural network to basically design their ultimate aerodynamic shape. And the last bit from me, I said that I would talk a little bit about this. I absolutely love this. So this one on the left here, this is something called it's a hyper-cavitating aerofoil, which basically means the underwater foil is cavitating all of the time, because that was the limit in underwater foils. This is why the AC-75, the America's Cup boats, they have a finite limit on the speed. The new technology is these super cavitating aerofoils that allow you to break this 60-odd knot barrier. Now, the current world record is done by this one on the left, which was a fixed wing boat at 65 knots. And you can see it was a pretty rough ride at that point. Now, to break that, you've really got to look at the minute details of improvement, and you've got to take into account aerodynamics, fluid dynamics, cavitation, structural side of things. So there's a big multi-physics problem that you've got to take into account. What this XP80 team are doing is they're building a neural network, taking all of these multi-physics factors into account. So they're feeding it lots and lots of data at the moment, both from experimental and virtual data, to come up with a neural network that's going to be able to help them design this boat. And I've seen the mock-up of this boat, and it looks small there, but it's actually probably bigger than this room. And this boat is going to, they think it's going to break 80, they're saying 80 knots, they think they're going to break 100 knots with this thing, because depending on how big a sail they're going to use. So you can see the size of that sail. Again, students, you put them in there, they're fine. So this is a great example and something really exciting. So this record attempt, the boat's going to be on Lake Geneva later on this year. The full world record attempt is going to be early next year. That's it from me. I put interrogation there because I think we brought something pretty new to the environment. I expect lots of wonderful questions coming out. I don't know whether I'm supposed to field questions now or whether I'm supposed to wait till later. But
you're going to be on the panel after.
Yes.
At the end of the, yeah, that's great. Yeah, I mean, if people have got a burning question that they might forget in a couple of hours, then fine. I think if we hold it, we can come in on the panel. That'd be great.
Okay.
Thanks, Andy.
Brilliant. Thank you.
Thank you. That's great. That was spirited. Thanks, Andy. Yeah, I mean, for me, I think you're right in that the AI world has been around for a while, but you found a little niche here where I pick up this this thread of time. You know, time means a lot in terms of commercial value. Of course, it does in that space.
Yeah.
So yeah, that's really good. Thank you. Yeah. So how are we doing on timing? We're good. Okay, so now I'll hand over to the next speaker. That's pretty well on the nail actually. So Sean Lang, Alistair, there you go. So yes, from evolution of simulation and data democratization.
Yeah.
I got that right.
Yes, certainly.
Okay, thank you very much.
Thank you.
I'll leave you on stage. Thank you.
I'm super impressed with how effortless Andy's transition between the slides were there, as much as everything else, Andy. I hope I'm going to be able to do this just as well. Okay, great. So thanks for having me, and thanks everybody for joining. My name is Sean Lang. I'm a data strategist at Altair. Altair is a company we've been around for 35 years or so, been in many different spaces throughout the years, and data for us as a company, much like for the world, is the next frontier. That's something we're very excited about. So my role is working with a lot of Altair's engineering clients and partners here in the UK to start to embrace data and get these companies adding value from data, not just adding another buzzword and another thing to their repertoire. The purpose of the presentation today is really about the democratization of data, and we see that as being the next big thing, and how to actually make artificial intelligence work and take it off slides and take it into return on investment for organizations. And I'm going to trace back the democratization of simulation as well, which Andy has mentioned as well in this first presentation. Okay, it works. So to frame the discussion, we all know that artificial intelligence works. We've read the news, we've seen the articles, we've seen all the statistics. The first one here, Capgemini saying that auto OEMs can boost their profits by 5 to 16% by deploying AI at scale. We saw Citrix and McKinsey in the last year calling it the single biggest driver to organizational growth today. So the potential, the opportunity is very well covered. There's some great movies about it as well. But in artificial intelligence, we are approaching this sort of inflection point at the moment in terms of the people to actually do the work and to bring this potential to life. Forbes have said that in the US, there's currently a shortage of 250,000 data scientists. The UK government released their AI report in November last year, and they said in the UK there's a shortage of 110,000 data scientists, and that every data scientist role, or 69% of those roles, is what they said, were very difficult to fill. So with all this potential, with all these use cases, with all this interest, if we don't have the people to be able to do it, how are we going to achieve? But a data scientist, they're well known to need 3 particular skills, and they're the skills on the bottom left of the screen. It's known that a data scientist needs computer science background. It's known that a data scientist needs a mathematical and statistical background. And it's well known that a data scientist needs domain expertise. And if you look at those 3 bubbles, if you think about the engineers in the room and the engineers in our companies, they very easily fit 2 of these 3 bubbles. They all generally have a mathematical and statistical background. They certainly have domain expertise. They know their products best. They understand what makes them fail. And of course, they don't tend to have this computer science background. They don't have data science degrees. They don't know generally how to code complex models and use libraries. But with the technology that we'll show today, and which I'm delighted that Alistair Grimshaw from ProDrive will also speak about, that difficulty in learning computer science is less and less a difficulty. And that's because of the democratization of technology. We've heard that about simulation over the last few years. We heard that about everything. A computer was very difficult to use 30 years ago. Now it's used every single day on our laptops. So not only are they the right people for the job, the engineers, but they're also in plentiful supply. The European Commission saying that there's 3 million mechanical engineers in the EU today. So they really fit this bill to embrace this technology. And a great conversation already this morning that we know that AI works. Technology has been around for quite a while. It's now about a cultural shift. It's about changing mentalities. It's about getting engineers, people in our existing companies today to use the technology available to improve their products, to improve their projects. And that's really the end goal, of course, for data. It's not just ourselves at Altair that think this, it's also a lot of our clients. And one of our big partners on the data science side is Rolls-Royce. They see a very similar perspective. Rolls-Royce have created what they call the R² data labs. They've put in about 80,000 hours of training over the last 2 years. They've trained about 20,000 people in their organization globally on the basics and methodology behind data science. And what we've been working with them on is within their engineering department, specifically within their jet engine production process. So as we've seen, there's a huge shortage in data scientists. So them creating the R² data labs, it can go some way to doing some really nice niche and complex projects. But Rolls-Royce is a company, they'll never survive, which is 100 data scientists when they have tens of thousands of engineers. So it's all about getting them to understand this and getting them to really push forward this initiative with the return on investment that Capgemini and other analysts have been promising us. So Rolls-Royce, the production of a jet engine is a multi-step process. Much like Airbus, it takes many, many years to produce these things. It's highly, it can be quite manual, it can be very expensive. And what Rolls-Royce are giving them engineers now is to see where are the anomalies and to be able to find these anomalies much earlier in the process using this type of technology to accelerate that production process. So all of this talk about making artificial intelligence easier with technology today to get more people involved in the conversation, it reminds us of what we've seen in the past with the emergence of simulation and computer-aided engineering and the embrace of that over the last 30 years or so. In the 70s and 80s, simulation was a topic. It was sort of invented around then, and there was tens of scientists, maybe a couple hundred of scientists around the world. It was really driven in academic institutions. It was driven as open source. In the 90s, you started seeing companies like Altair being created to start to build easier solutions that more engineers could use the power of this technology. It was taken out of just, let's say, the coding realm. So in the 90s, you saw this incubation, you saw a growth of users. But then in the 2000s, you saw the start of a democratization. You started to see it leave the center of excellence, let's say, and go to many more users. And now it's sort of an imperative that most engineers coming through university are being able to use simulation. And that's not to say the core experts are no longer part of the conversation. You have the methods team within a lot of engineers who do a lot of the verification, and whereas you have the vast majority who can then build these models. And it's going to be the exact same within data science. And I can see in 10 years' time it being an imperative for engineers coming out of university to be able to understand data science and use it within their daily workflows, just like we see that with simulation. And I guess, why is this important? As Clive Owens, who's the head of the Center of Excellence for AI at Jaguar Land Rover, he said that every use case JLO are doing brings in 96 times the return on investment. Every AI use case they do, 96 times the money they're putting into it. So if you get more people involved in this project, you're going to get more projects and you're going to get more return on investment per project. And that, of course, is really where Altair as a company lie. We as a company have helped on this democratization of simulation. We understand where it's successful, where it struggles. And we do see this democratization of artificial intelligence and data science being really on this same trajectory. If we look into this product development lifecycle, you can see here the amount of data sources, both physical and real data sources that there is today. You see data on demand. This is synthetically generated data from simulation models, which has been around for quite a while. You see data in hand. So data in hand is generally coming from
outside this ideation and concept design stage, and more from the engineering and manufacturing stage. You see data coming from your ERP, your MES, your SCADA systems, your historians maybe, but also from a gluttony of different silos of text files and PDF files and Excel documents. We work with a company called KLA. They make a lot of the semiconductor machines that Samsung and all the different fabs will use. And they had all of their suppliers selling all of the subcomponents for their machines. We're sending them data in PDF files and text files. Then they also had all the files from the health of that machine, log files in text information again, and looking to be able to strip all of this information into rows and columns so they can amalgamate this with data from this ideation phase. Maybe it's the CAD data, maybe it's the modeling and specifications data, all together. What we really see at Altair, and of course, much like what Andy was saying, Altair's heritage is in simulation, and we are bringing artificial intelligence to that to be able to predict the shapes and geometry. But for us, which is completely next frontier, is this in-service information, is information from sensors on the manufacturing line, information from sensors on the vehicles, and information from sensors on the planes. There's a huge amount of physical data now from the quality of the end product, from warranty claims, for instance. And this data can be really plentiful and can really help on this product development lifecycle. As you see with the arrows, everything is feeding each other. It goes one way, but the in-service data is going right back then into the ideation phase. To give an example of some of the quantities of in-service data, another company we're working with at the moment is Renishaw. They make the 3D printing machines. And for every run that they're doing, they're creating about 100,000 records per second, which is about 1.5 terabytes of information every single hour that Renishaw are producing products. It's a huge amount of information there. So throughout this product development lifecycle, you're now seeing data on demand. From simulation, you're seeing data in hand, this historical information, and you're seeing data in the fly. And you really need to be able to amalgamate these sources together to be able to produce better quality products at a much faster and accelerated rate. If you look at the use cases around this life cycle, there's so much. And this is combining the sort of stuff that Andy was showing around concept creation and model build and design optimization, but also then going from after that product is designed, when it's in its life cycle, looking at product quality, looking at predictive maintenance, looking at cost reduction, looking at customer satisfaction. And the use cases are really endless. And as we said, this is a mentality shift. Once engineers do one use case, understand the value that this can bring, the opportunities that it can present are so plentiful and so widespread. What Alistair Grimshaw will be speaking about is a little bit around this sort of customer satisfaction. How can we best understand what's going on with our vehicles so we can feed back these insights? Cost reduction, warranty analytics, I'll speak a little bit about later. We're doing a project with Jaguar Land Rover at the moment on warranty analytics, which they'll be speaking about in at our customer conference at the end of May in Warwick. But again, there's so much data now from the actual life cycle of this product that can be translated back into the simulation and back into the design. Being where we are in beautiful Silverstone, I wanted to, of course, speak a little about the use cases for data and machine learning within the racing context. Again, Andy has shown you some really great use cases within that simulation workflow. What I wanted to focus more on is within taking the physical data from the sensors, from the vehicles, from the runs, etc., being able to understand what's happening in the real life to then bring back into our simulation. Again, everything being done by engineers. Engineers are the ones producing the vehicles. Engineers should be the ones understanding the in-service data coming from these vehicles. If you look at a racing car and the objectives behind racing analytics, it's of course to increase the speed of your analytics. It's all about being able to understand what's happening in real time with sensors on the vehicle. It's all about trying to alert when critical parameters, let's say, go out of range. It's all about trying to build machine learning models on historical data to be able to say, okay, in the past this happened, so in the future when metrics, when temperature or pressure or vibration goes too high or too low, these are the types of responses that we should be pushing. Of course, that is a beautiful picture, but also if you look at the racing world, there are some huge challenges in terms of that volume and velocity of information that's being produced. On a typical F1 weekend, you've got about 150 sensors on a Formula One car, produces about 0.5 terabyte of information a race. At HQ, you're producing almost 10 terabytes of information every single week. So a lot of design changes, a lot of data being produced. With this streaming data, that it tends to be, like I said about Renishaw, far too big in terms of volume. There's a lot of processing and preparation of that information that has to go in into the process. And this is really what you're going to see here: prepare, monitor, model, and optimize. And before I bring Alistair onto the stage to speak a little about what they're doing at ProDrive using our tools, I thought I'd show you a quick demonstration of how you could take some of this racing, in-service, IoT, biometrical, environmental data to be able to understand what's going on in the real world and then translate that back into the design of our vehicles. What's quite interesting is, you know, as we've said a few times, AI and data been out there for a long time already. This solution was actually developed for the capital markets industry. And for the last 15 years or so, all the big investment banks in London, all the big investment banks in New York and Hong Kong and Singapore have been using this tool to process information coming from stock exchanges, market data providers, banks, and being able to build models to understand what to invest in as fast as possible. So a lot of time series information coming at quite high velocities. Of course, the world of racing is just the exact same. A lot of high frequency data looking to make decisions as fast as possible on strategy, lap time, pit stop, all of these things. So you want the real-time view, but you also want this historical view. So here you're looking at different laps, you're actually zooming into particular parts of a lap, you're comparing cars, you might be comparing races, different years, different drivers. And here again, more historical data on lap averages, fastest lap, understanding where the weak points of that vehicle, and again, bringing this back into the engineering teams. The amount of use cases that you can do with this tool is obviously very widespread. Here you've seen it on the track. It's also used a lot in the wind tunnel. It's used a lot for driver classification. There's a lot of teams that are building machine learning models to actually classify who are the best lineup of drivers next year. But it's always better if somebody else comes on and speaks about things. So I did want to invite Alistair Grimshaw and thank him, of course, for coming on the stage to speak a little bit about how ProDrive introduce us to ProDrive and tell us how they are using our technology.
Hi, so I'm Senior Analysis Engineer, ProDrive Motorsport. At the moment, we've got two primary programs. Top is for Aston Martin. We run their sports car programs in GT. So these are modified road cars, very heavily modified in the case of those. So 3 categories, GTE, 3 and 4. 4's close to a road car, GTE's very little of the original road car is used. The picture there is us winning 2020 Le Mans 24. We finished first and third, across the line in nice formation for the photo. These cars, probably at GT level, we're logging about 1,200 channels of data. This combination of physical sensors plus internal channels generated on board, states of control systems, internal maths to try and do some physics on the car to predict car behaviour in real time on board. And we'll get that data back in the pits over wireless telemetry link. These days we use a 5G mobile data link. In the old days it was a radio link. And we also, when the car comes into a pit, we're able to offload data, far higher bandwidth, a lot more data as either during testing practice, we'll be plugging an Ethernet cable literally into the car and getting the data off. During a pit stop, we have a ruggedized USB key. Sounds daft, that we literally swap in the pit stop while we're fueling the car, and we get the data from the previous stint, so we can then spend the time in the pits looking at what's happening on the car. Longest event, big crown jewels of the 24-hour races. So Le Mans 24, as I say, I was winning a couple of years ago, our class. The Daytona 24 in America is probably the second biggest race. Plus some slightly short races, 12 hours of Sebring, which we did last month. Get around, and we also, it's not just us as a team building racing cars, we also sell these to other customers, teams, who then go racing with them. Again, that's primarily GT3 and 4. We have customers all around the world. These cars raced in everything from the New Zealand GT Championship, the IMSA and SRO series in America, in Australia. We ship cars all over the world, and hopefully I'll explain what we do with some of the data we get back to try and help our customers. The other big program, slightly more recently, we're only 2 years into this program, is for Bahrain Rally Extreme. This is a blank sheet of paper, off-road tank pretty much, for the Dakar Rally, the FA Cross Country Cup. There, we're more limited by regulation. We don't get the live data streams from the car. All we do is get, at the end of a stage, the opportunity to get the data to offload the car. Slightly less channels, partly because of regulations. There are big limits to try and stop teams as doing clever stuff. So you're not allowed wheel speed sensors on each wheel, so you can't do traction control, etc. So, for say, it can be a bit of a challenge trying to work out what you need to do, because there's a whole bunch of people in the governing body who try to stop you getting the information by regulation. Longest event, Dakar, that's 12 stages, 39 hours of racing over the desert. So these are big, long events. Gotcha. So in terms of data analysis, so historically, each car has its data logging system, maybe two. Often you'll have a logger car that looks after the chassis side, one for the ECU, and each system will have its own proprietary data analysis software. The top ones for the Bosch systems that we run on the GT4 and the Dakar. The bottom is iToolbox for the Cosworth systems on the GT3s and Es. These are really good optimized tools if what you want to do is what's historically been done in racing, which is look at how's the car this lap, the previous lap, has the driver brake too late, has he brake too early, where can drivers find time, and if you want to zoom on an individual event, the driver's complained the gear shift car didn't work properly as he was shifting down into the hairpin. You can zoom right in on data in these tools, very detailed, plot what you want to see what you want. What they're not good for is, partly due to literally the size of the data sets, is looking at longer term analysis. We're a little interested, the next step up is obviously the whole of the 24-hour race, the whole of the 12 hours. These tools struggle somewhat with these, so that's where Panopticon was coming and Altair. So when we first started moving away and hitting the limits of the tools, the next stage of the workflow was we could use the proprietary tools to export manually into Excel, data tables of aggregate data. Obviously, if you're doing racing, the obvious aggregation is on a lapwise basis. What's the maximum fuel pressure? What's the minimum fuel pressure we saw around the lap? And the earliest workflows were literally copy and pasting from Excel into Excel from Toolbox. So we then moved on a bit. Next stage, both Bosch and Cosworth introduced data access objects that we could use to get our log data, get it out of their systems and into whichever environment. Originally, we went for MATLAB, but then to try and, because of MATLAB licensing, etc., we then moved to Pandas, Python, so that pretty much anybody could install it all open source. So we can get an aggregate of an entire 24-hour race. The plot at the bottom is this year's Daytona 24. That's actually the oil tank level in the car that I was running, which is a customer car, Magnus Racing. We finished second. You can see the car used a bit of oil through the stints, and 3 times in the race we just at a pit stop have to add oil under pressure. We put in about 1.5 litres. The actual scale of that isn't true litres of oil in the car due to its dry sump system. There's oil in the engine and in the tank, but we know how to read these data. The odd spikes are when there's a safety car and the oil level in the tank changes because the RPM profile of the engine changes. But suddenly you've got whole visibility of a race. That's quite an obvious example. We'd be looking at that in real time, but there are other examples that don't really want to share where we can pick up things post race by plotting the whole race and look at things that might need to be addressed for the next race. So one example, I haven't got a plot of it, would be the fuel pumps in the tank. Changing fuel pumps is not a great job. You've got to break into the fuel system, drain all the tank. It's messy. The mechanics don't like doing it, and then you've got to be really careful sealing it all up. So we don't like to go in there and mess with fuel pumps, but we understand, we've been doing it for quite a while, the current characteristic of the fuel pump in the tank. When it starts out, draws a level of amps, then as it wears in, for most of its life, it draws another level and then starts to ramp up as it's approaching failure. So we can pick up from longer term plots when that potential failure of the tank, and then before the event, so we can say that fuel pump needs changing for the next event, and then the boys can do it controlled at the workshop rather than potentially dealing with an on-track failure. And we can also do those sorts of plots with data we get from our customer support engineers who go out to the teams and feed back the data, do the same plots, and we can advise customers this component based on what we've seen of its running is potentially coming up to life. You might want to think about changing that. Sometimes they listen to us, sometimes they don't. It also gives us, obviously, I don't know if you've done any Python pandas, but one of the big problems is with all the graph plotting is they're all done in code. You're in there having to modify scales, etc. Panopticon, by going, it takes our existing pandas data sets, we just switch them in there. And then so there's a nice front end that people who can't code can produce the plots they want. Pretty much any of the customer support engineers, not all our coders, can generate the info they want, and then we can show that to customers. It can go to senior management to convince them of items. And just one more example from Daytona, again, of a very clear event. This is the gearbox temperature around Daytona for this year. That's the whole 24-hour race. You can just about see during the night when it got ridiculously cold. It was quite cold during the day. You'd think Florida's nice. It was near freezing, 2 degrees C overnight. So the gearbox temperature went down a bit, and then suddenly here we've got a massive spike up in the gearbox temperature. What had happened is the driver, we saw it on TV once, the TV director caught it on the replay, showed us the replay. He'd been backed into the wall by another car. The tailgate flew off, and the gearbox cooling duct runs off the tailgate, and it moved the duct, so there was not enough air getting through. Ran very hot for a while. Next pit stop, it goes back down because we managed to repair it, fix it in place. And obviously the cooling's worse because the airflow around the back of the car is worse without tailgate. So there's a little rise until, again, not about 4 hours, tense moment when suddenly the gearbox temperature shoot up again. We're watching this in real time, much discussion, and the duct had managed to work itself loose again, simply because of the pounding going around the track over the curbs. But again, at the next stop, repaired it, made the finish quite happily. Again, the odd down spikes, so where there's a safety car, where the car's doing a different pace and temperature characteristics of the car change. And in that case, yeah, we were second in class. So again, a successful race, helped by data. Spending 24 hours watching numbers is an interesting experience, but really it's a question of keeping the car running. We do other performance analysis stuff, although within sports car racing, you're quite limited thanks to the governing body, try to balance all the cars, so whether they're front engine, mid engine, rear engine. So if we start getting too clever and finding a lot of performance, all they do is take away our performance. We can find the second allowed, and then we get an engine adjustment the next race to take it away again, to keep all the cars nice and balanced. So a lot of the work we do is focus on things that aren't performance balanced, which is health monitoring, keeping the car running at its best at the level that it should be able to perform, because that doesn't show up, that won't be taken away from you. And similarly, there are other stuff don't talk about in terms of we do with strategy, etc. Again, because that's not balanced for performance, whereas doing new aero, new more engine power, it'll just be taken away from us, and therefore it's dedicating our resources to that area isn't an effective way of increasing our race performance, even though it would theoretically improve track performance. So,
Thank you very much, Alistair. That was awesome. So Alistair will be on the Q&A at the end as well. If you want to ask him any questions, of course, he'll be around all day. I'll just finish off really by talking about outside of the world of Formula One. Very similar types of challenges exist everywhere. This is a framework we're working on at the moment with a partner around trying to completely eradicate warranty in the future. It's all about hybrid data streams. The concept of a digital twin. My sister actually had real twins just last week, two little lovely girls. Obviously they come out at the same time, so they're absolutely physical twins. Whereas the concept of the digital twin is slightly different. You obviously have this virtual twin initially when you're trying to create this vehicle. And what is designed is never actually produced, because there's always going to be some sort of deviations and variability. With the concept of the physical streams that we can get off manufacturing now from assembly and scanning the vehicles, we can feed this real life data, even from the telemetry and the sensors on the vehicle, back into this virtual twin to create something that is as close to as possible the complete and utter copy of what is going on in real life. So once we get new warranty claims in, we can identify where in the process that fault came from. Was it from the design? Was it from how the car was being driven? And be able to find the root cause and alleviate that through predictive maintenance and the design of the next generation vehicle. JCB, their devices, their assets are used in many different ways, oftentimes outside of the duty cycle of what they were designed for. So if they're getting a warranty claim for somebody that was using the machine incorrectly, of course that invalidates that warranty. So that is a really great way, again, to combine these hybrid data streams. Jaguar Land Rover, as I said, are going to present May 24th in Warwick on this type of use case as well. There's a video here, but I'll skip past it and maybe just go to the last slide, and then I'll come back one. Just talk about today's product being increasingly complex. The video that hopefully you'll get this slide deck and you can check out. It's actually creating a washing machine, and the washing machine has about 25 sensors on it, taking in temperature and pressure and torque and vibration and all of these different things. And again, they're looking to understand what metrics and in what type of environment will these washing machines fail. And once they understand that from the in-service data, they can bring this into the design of the next generation washing machine or oven or any other white goods that the company Modal produce. Here you see the beautiful Dakar car from ProDrive. And we spoke briefly about Renishaw. We spoke briefly about Rolls-Royce's jet engines. On the left is a espresso making machine from a company called Gruppo Simbali. It's great going to conferences again. Last week I was at the London Coffee Festival. Quite a different type of event, but equally interesting. And Gruppo Simbali were presenting with us there. Again, making these really complex coffee machines with fluid dynamics, thermodynamics, and many other complex systems that goes into creating this system. Again, 20-25 sensors on it. It's really important to understand when they fail to create this most identical digital twin. Again, using this sensor data in real time, with the computer generated during the design. What we always say to our clients as they launch into this process is to apply this approach, which is this what we call the CRISP. Well, it's well known as the CRISP GM approach. It's been around for quite a while, but it really gets people thinking about what is necessary before we launch into AI. And the first thing is always business understanding. People do AI now for the sake of doing AI. For me, there's no people start looking for AI use cases. That doesn't exist. There's no such thing as an AI use case. It's a business use case amplified by artificial intelligence. So what are the challenges for our business today? And in Mobil's case, it was trying to improve their customer satisfaction, increase the uptime of their machines. In terms of the data understanding, what data do we have? Okay, we've sensor data. Okay, we've maintenance records. Okay, we've error codes. How do we prepare this information? Well known that data preparation is 80% of the process of building machine learning model. So it's really important. The modeling actually, when it comes to it, is relatively easy. You saw some of the solutions today. They're low code. They're very quick to produce these models to find something that fits as accurate as possible. And for deployment, you saw a little bit about that now. It's all about real time. There's no point understanding what happens 5 minutes after the fact. It's all about trying to make this as fast as possible. So that was my presentation on data becoming easier now and really becoming into this world of engineers after they've already taken up simulation tools in the past. In terms of what's coming up for Altair, May 24th, if anybody is around Warwick, the British Motor Museum, we'll have BMW and Jaguar Land Rover and JCB and many others speaking about their partnerships. At the end of June, we have our conference where I'm going to hopefully try to drag Alistair as well too, which is virtual. It's called Future.ai. And I'll be around, as I say, for the rest of the day and the Q&A if you have questions. Thanks very much.
Thank you, Sean. Thank you, Alistair. Again, I think that the good thing here, it gives a real awareness just by that real fascinating introduction topics there. You know, we're living in a world now where we're getting data. And you know, it's interesting to see how almost exponentially the decisions are being made from data. That to me is the real takeaway, and I think that's been probably a good insight to a lot of people. So it's all about now data, making decisions quicker. So good. So to take us up to the coffee break, I'd like to introduce Ross. Ross, very good friend, obviously. I've got to be careful, get a bit emotional here, because maybe we certainly probably this be the last SIG you'll be in the role that you're in attending.
That's right.
So I'd like to just give Ross the floor a little bit for 10 minutes before we have the coffee, just to talk us through the AI residence program. Right. Thanks, Ross.
Oh, I see, yeah. It'll move on in a minute. It doesn't, it's okay, it's all right for a minute. Yeah, so thank you for having me and allowing me this opportunity, because I'm Commercial Director of Silverstone Park and I'm Chair of Silverstone Technology Cluster for 2 more days. I've worked for MEPC for 15 years, 8 years at Silverstone Park. And I've been chair of Silverstone Technology Cluster for the last 5 years, working with Pim and David and Mark's in the room, a few other board members, and was involved in helping to set Silverstone Technology Cluster up. So it's really nice to get here today and have the chance to talk and be involved. I am going to be an STC ambassador, I don't know what the right analogy is, but I'll keep coming back anyway for better or worse, and get involved and support all the things I really believe in. And this special interest group and the work that it does, it epitomises one of the parts of the vision for Silverstone Technology Cluster, because it's about bringing other thinking in to, you know, what's traditionally a straightforward engineering, advanced engineering world, and saying, let's bring data in, let's bring cognitive technologies in, and look at the opportunities when you bring engineers and data scientists and the like together. And I was talking to someone on the way over earlier who was saying, in terms of science and research now, the world is changing. Gone are the days when you can be the chief exec of a startup business and understand and be in control of all the different aspects, because you can't be a data scientist and a life scientist, for example. And so it's learning about, these roles that these key people are going to play in industry. And for me, it's about that collaboration. And I can remember when in Cambridge back in the day, 20 years ago, we were talking about life scientists and mathematicians getting together. They're like, well, why would they ever want to talk with each other? And then, of course, bioinformatics was born, and the mapping of the human genome. And, I think as well as solving the world's problems, we're also here to make money and be successful, grow the economy, employ people, pay our bills and our taxes, and make the world a better place for young people coming through, so that they've got, somewhere to work. And I think there's massive opportunity in doing things differently, because that's the definition of madness, isn't it? If you keep doing the same thing and expect something different. So do different things by bringing people together that don't necessarily work with each other or understand each other, and see what comes from that. And as a sort of science part practitioner, call that engineered serendipity, which I've said before on platform. That's what it's all about. It's getting people together, giving them the opportunity in special interest groups, annual conferences, through PIM, making those connections between you all. People say, I don't know, I just feel like I should know more about X. Who do I speak to, PIM? And getting him to help you to do that. So yeah, to that end, really, because I, as well as liking to talk about it and the strategy, I like to do it because I think that's the fun bit, really. So what we've done over the last 12 months is work with MKAI, and if I can get this next slide on, you might have the magic touch. Again. There we go. There we go. So to sort of talk about the subject matter that you're interested in, and following on from your presentation there about, how do we apply this? I thought, well, where better to start than with my friend Richard Foster-Fletcher at MKAI. And MKAI are a global network of people interested in cognitive technologies, but the guy that runs it is based in Milton Keynes, so it's just up the road, and there are a lot of local people interested in this stuff. And by the way, one of the things that was said in the SQW report when they did the mapping of, is there a cluster here? One of the things they said we should be doing is helping the engineers that work around the Silverstone cluster to work with the kind of software engineers and the data people in Milton Keynes. So what I did was I said to Richard, can we do something together where you become a sort of AI in residence and for Silverstone Park? And if I can get 6 of our best sort of engineers, senior engineers, can you put that into their minds? Can you just expose them to it? And the bit that was really fun for me was ringing people like John Hilton and Rob Lewis and Simon Dowston saying, do you know anything about AI and virtual reality? Have you put one of those headsets on? And someone else in the office has done a bit of that, Ross. Yeah, we've got a headset somewhere. Or well, no, I don't really know anything about that. And it was great to sort of think, okay, great. So you've got this fertile mind, you're a problem solver, you're highly successful. I want to plant all this stuff in there. And we had this sort of introductory meeting where I got Richard in, a couple of his colleagues, and the guys from Silverstone Park, the ones that run these businesses on the list here. And I said, we're going to pay Richard to work with you, okay? And you don't have to get anything out of it other than to please just have that explorer mindset and be open-minded and be exposed to these ideas. And by the way, the stuff that you find out about through this process doesn't need to be relevant to you today, but it might just stick in your mind, and there might be something that's then relevant to you in the future. So this is news just in, really, in terms of the results so far of that sort of pilot year And so you can see that Danica's using mixed reality prototyping to reduce errors. 3C test, which do the electromagnetic testing work. They're looking at proof of concept and data extraction and transformation. Richard would be good to come and these companies to another event and tell you the detail. You can ask them questions about it. You can see I'm just reading off the script, but I'm excited about the fact that I have been involved in some of the conversations and they've been wide ranging. I suppose what I said was, think about your building management, think about climate change and your carbon footprint. What about processes that you have to use in your organisation? How could they be used, or how could they be enhanced? What about your customer experience? How could that be enhanced by using cognitive technology? And then the nirvana for me is, there's so many products that you could develop out of this, that you will make money from and will create jobs. So KWSP are looking at smart factory with the work they're doing at the Digital Manufacturing Centre. They're looking at potentially putting a hackathon on. And again, it's about bringing different perspectives in, different people to work with their people and mix it all up and see what good comes out of it as an experiment almost. Lunaz with the work they're doing on converting classic cars and recycling trucks to electric, looking at IoT for predictive maintenance. Delta looking at the battery optimization, and then Flybrid with the real-time feedback to make adjustments to the equipment that's out. They're doing quite a lot of work at the moment, Punch, in the construction sector. So there's just an experiment that's been going on for the last 10, 12 months. And Ruth Williams, who works with me here, will work with Richard to kind of look at next steps with that. And I think him and the board should look at that as well and see, what can we learn from that work that we did over the course of the last 12 months. So hopefully there's some exciting stuff that can come out of that. So I know we're nearly at coffee break, so I'll just finish by saying that Chris Sills, who is somebody that works at MEPC already, is going to take over from me as commercial director, and he'll come to events, he'll talk with Pim, he'll look at joining the board and being fully involved and very, very supportive of all the work that's gone before, and to continue that. That's absolutely the sentiment. And like I say, I'll be an STC ambassador, and what I'd like to do is look at who else are ambassadors and what they're doing and how we can help to work together to help grow Silverstone Technology and continue the work. So yeah, finally, I just want to really say thank you so much to Pim Van Barsen and to the STC board, because none of this is a single person, is it? It's like I was saying about the collaboration on new ideas. It's about people in the audience, the faces that I recognise, the people that have turned up and supported and got involved with this. That I really appreciate that, and I've absolutely loved working with you. Very torn. I'm going to Norwich Research Park to be chief exec, and it's a career move for me, so that's why I'm going. But that's the only reason. There's nothing I don't love about this place. It's got that buzz, so I just wish everyone well, and look forward to continuing to work with you. I'll bring some plant scientists over and we can mix it up again if you want. Okay, thank you.
Thank you.
We're on coffee break now. Sorry, we okay with 15 minutes? I think we're 5 minutes over. So 15 minutes and then back in here. Then we've got one of our colleagues from Hexagon coming in remotely, who's got the final presentation. Then we'll hand into the workshop a bit later in the panel and talk about all the stuff we've learned today. And then questions, burning questions for the team. Thank you. All right, free coffee. Good to see the eyes light up again after we've had a bit of caffeine. Always good. So yeah, look, the last specific session, interest session, really, before we get into the questioning panels, and then we can head towards lunch and the networking after that. So I'd like to now just hand over and introduce to colleague in Hexagon, Kambiz, who very kindly has used and exploited the modern technology of presenting in a virtual way on his vacation. So thank you very much, Kambiz. So I'll hand over to you, and this topic will be solutions for real-time predictive modeling and manufacturing. Thank you. You're all.
Thank you very much. Thank you, Dave. So you can see my screen, everything is fine. I can start. Hello, can you hear me?
Yes, we can.
See you.
Okay. And you can see my screen.
Yes. Thank you.
Okay, perfect. So good morning, everybody. Thank you very much for listening to this, this more or less, I would say, deep dive into some technologies we can currently provide around AI. Now, I will obviously not be able to tell you about all the activities, but I think I will cover around 20% of what happens for us that I am a part of this R&D group, and as you can see, well, we spend a lot of budget on the R&D. 10-12% of our turnover goes into that, and that means nearly all domains are interesting for us. Now, in particular, what is probably more relevant to my talk today is what happens at Design and Engineering business unit. This is more or less where simulation technologies are concerned. A lot of you know software from solvers, add-ons, Nastran, Mark, etc. These are in this business unit, and this is where I belong. Now, my presentation will have essentially will cover three topics. One, a very generic discussion on system monitoring, complexity management, which I will be using as an introduction into what machine learning and AI actually is and does. And I will give you some examples of what we can do today, more or less industrial applications based on images. So learning from images and designing based on images. And finally, I will present to you everything we do around CAE, optimization, and similar solutions which you more or less saw this morning. So what comes into what is new today in the application of machine learning is that it is becoming a bit more or less a horizontal activity. Well, previously in starting as from 1950s, even earlier, machine learning was actually operational and known. Most of what we do today was actually known before. It's just that it's more easier to do today. But it's becoming something in common. It's becoming a horizontal technology which covers all the various industries, the energy segment, healthcare, smart cities, transport, of course, and a lot more. And this is really the common point. This is the new, I would say, the new phase of machine learning and AI. Now, what do we mean by this machine learning AI? Well, we need essentially the three topics I have mentioned. We mean that we are capable of exploring the process or many processes simultaneously. We are capable of collecting information from those processes, and then we are capable of analyzing. So when we say we are doing machine learning, AI, etc., all these buzzwords, we are actually doing this. And you see, you are already doing it. More. So there is nothing really new in the sense that it's not a magic science. It's just I would say more modern way of looking into it. Now, the data which we need is no more, I would say, a barrier to doing this, which was probably earlier on. We can handle any type of data today, scanners, images, CAD files, time series, etc., animation files. We can use many techniques on what we generally call AI, ML. I always add the term wrong, you will see why. But there are so many techniques available that that we can actually be selective even, and we can have our own preferences. Now, there are some topics which are very much related to this, like sampling, since we are talking about data. So we also need to think in terms of which data do we collect. It's not because we have data that we have information. The real value of machine learning is collecting the information-rich part of the data. So it's not all data which is interesting, it's only parts. And then, of course, all this will serve modeling and so on, but modeling we can already do, testing we can already do. So why do we want to do this? Essentially because we want to find the best solution out of a system, and that's what we call optimization. So these are all relevant, and they are open to all sorts of end users, like engineers who do their traditional design and development. These are also open to developers. So we have suddenly a sort of close collaboration between developers, those people who script and automate things, and people who do design. We also have people from design level, that means people who never do computing, who never do simulations. They can now have access to more or less same level of design capabilities, not necessarily competence, but capabilities that the design engineer has. And of course, methodology development is also integrated, because we have all these people who actually work around the same project, but we have more or less found a common language between all these people. And you see for the first time that in a company we say AI, but we don't necessarily say AI for what? We just say AI ML, which is a little bit confusing, but it's also because it's a generic tool. Now we know what design is. It's more or less straightforward. You need to make a decision, you have data, and you have output. Now, when you collect the output, well, there is a decision to be made. The only issue is that, well, this output, which I've represented by function F, is in reality a complex process itself. So this output is not just a black box. It's assessing parameters, variables, geometries, properties, loadings, a lot of things going into modeling, solving, and so on. And at the end, what comes out is that response, that output you're looking for. So essentially, what we want to do by AI is to skip this middle part. We want to do something which goes directly from variables, parameters to responses. And of course, if we can do that, we can optimize. Now, here we see a lot being said about algorithms, which do a lot of things. Essentially, what we are interested in is the part of machine learning, which does detection, which does recognition, which does predictive modeling, and of course, further on, cognitive, reactive, etc. Then we go into autonomous domain, and that's another sector which is in transport, which is interesting in itself. I'm not going to cover that, but more or less I'm going to talk about these three. Now, these algorithms were known actually by the founders of algebra, and even by people who knew that there's a distinction between a model, algebra, and data itself. This picture I have on the right from early 16th century, you see two guys. The one on the right is actually using ABAX, direct tables of data, and doing design. The one on the right is using numbers, doing number crunching, etc., algebra, and so on. So we already knew that there are two ways of understanding physics. The only issue with the last 5-6 century is that, well, it's the one on the left which has been dominating because of differential equations and so on. We'll come back to this. Now, a lot of these techniques are also because of the work of many scientists, of course. They somehow combine many methods of predicting time series, basic ones, ARIMA, ANOVA, mixture models, Gaussian models, Kalman filter models. We come also to some interesting topics, probably initiated by Markov in early 20th century, which relate data to concepts from thermodynamics made by Boltzmann, by Higgs, and which end up with a brilliant guy called Shannon, which many of you will probably know. And this guy starts building up what we call today the information theory. Now, the information theory is essentially based on entropy. Now, what do we mean by entropy? We mean that when you have a system, and you have a system which you want to analyze, well, it has all sorts of components, variables, parameters, functions, constraints, criterion. I won't go into the detail and definition of each, but you need to somehow understand the system, not from a equation point of view, but from an interaction between all set of which you need to monitor at the same time. This means that the previous X and Y I showed you in the previous picture, it's actually a very complex set of data. But if you can do this monitoring, then you can always control the system to stay within what we call a risk zone or risk accepted zone, this green zone I have here, and try to stay within this system. Now, this is what that data analysis is essentially doing. And for automotive, of course, we also relate this to some sort of thermometers saying below this, above this, things will happen. So we need to control that. Now, again, from that entropy concept, we see that nearly all optimization processes are of course, some sort of are made out of a performance function. This is what we call here, I call here Y. Now my mouse has gone mad, it's just moving all over the place, sorry. The performance function, which I have here, but also some sort of constraint function. To give you an example, I want to go fast, but I don't want the engine to burn, to explode. So these are always two conflicting issues. And this means that I need to monitor not only one function of the whole system, but I need to monitor all of it. And this is the introduction I want to give to what we can do today if we look into the data. The only way of doing this, what I just said, is well, collecting data, I showed you earlier, and trying to understand the relation between these data. Now, this is the initial point of AI and machine learning, by the way. By machine learning, we actually mean this. Now, we mean collecting data and trying to understand not only but many interacting things in that model. This you can see in civil engineering. There is planning of civil engineering. You can see in simple processes, simple like tooling, like machining, manufacturing, where you can actually understand by looking at the shapes of the object, you can understand information which you cannot measure. How do you measure the shape? It's more or less a holistic concept. You can measure dimensions, but you don't. How do you compare one shape to another? But this is a concept which, if we could do it, we could use it as a design concept. The same thing for monitoring processes. If we can look into many aspects of the same production process simultaneously and relate them, then we can always go on by looking at the relation between those output, then we can distinguish between green and red zones and say, okay, what is the optimal configuration. We also saw in the previous speaker example of onboard measurement. Now with onboard measurement, we can do a lot. We can look at the performance, we can look at the interaction. The real issue is that entropy. We need to understand what makes the system go out of hand and what brings it back into an equilibrium state. And of course, our success is always related to that equilibrium state. This is what we call robustness, reliability, and so on. Now, these robustness, reliability involve many types of know-how. And of course, it is also one feature of AI today, AI and machine learning, which has many facets. And this is interesting. This is even fascinating. How horizontal and general purpose one single technology can become. It can be applied to signal processing, to CAE, simulation. It can be applied to images, sounds, any sort of information, and it can be exploited for manufacturing. So let me show you some examples of what we can do, for example, based on images, simply. Well, we can, I have here a few disks which are manufactured and which we simply want to select the best. Now, just by looking at the images, we can remove the ones which are faulty. We can remove the defaults. Now, this is more or less a straightforward process, I would say today, but this is something which we can do automatically, completely automatically, without the subjectivity of the observer. We can say what parts of the are acceptable, what parts are not. And you can see that this is possible by this curve I have down here. This is possible with not that many samples. Now, one of the important issues of machine learning AI is, well, how many data? We heard this morning 10,000 cases, but who has 10,000 cases? Who has even 100 cases? So this is an important issue. We need to handle the topic of sampling, samples, and how many samples are essential. And as I said, not all samples are rich in information. Now, we can use it for PCBs. You saw this again this morning. We can collect simply from images, some sort of manufacturing surface faults, collect them just by taking pictures, by taking images. And this will allow a whole production line to be suddenly over more efficient. This particular example, I have it from a customer manufacturing microchips, and they were available. Now it's rare. But they had something like 6% of these chips which were just thrown away or sent back to the manufacturer because they had some surface defaults. Now, these were not function defaults. These were just surface. The shape was rusty, scratched or something. But you see, this has a tremendous effect on the production and your benefit, your turnover. This was 6%. Reduced to 1% by just applying this technology, which is more or less simple. You will see a lot today what we can do in health and similar domains, health monitoring of humans. Here I have an example of 200 images of lung MRIs. Some of them are, here you can see the ones which are more or less in the blue zone are healthy. The ones which are in the red zone are unhealthy. Now we can, by simple techniques like classification, just go immediately and position your own MRI and say whether you're healthy or not. Now this does not mean that we know everything about your health. This means that we can accelerate the choice, the decision making. So this is the issue. You had also an example from mobile phone drop test. I remember this application we could do in 2015. We actually did it in 2015, and it is probably I would say extremely simple in terms of any operation which is repetitive. So when I say 2015, this means this technology is something like 6-7 years old, and it is well robust, it works. It has proven to be possible to, just by looking into videos, real videos or animation videos, allow to establish what is the response, what is the behavior of that plate, glass, and based on the response, just do the design. We do similar things by looking at shapes of tires. Here I have 8 profiles. We know each profile, what is the sound, for example, corresponding to it. Now, these profiles are very, very useful for classification. We can just use them for associating them to particular responses. And if I have a new profile to see what's the response, well, I don't need to go and calculate, model, or measure, or anything like that. I just relate them, and I have my response. So, which I didn't have before. And as I said, this is a design tool common between designers and engineers. Again, the horizontality of the solution is extremely interesting, because what I just showed you here, this tire example, well, it works perfectly well or as well for CFD. I have NACA profiles here. I can associate the shapes to a drag and lift coefficient, and based on that, only on that table on the right, I can do my design. My design is no more just measuring or calculating. It's just comparing tables, as I said, and here you can see that the outcome is very, very good. So the comparison is very close between analytical measurement, because these are simple profiles. We have analytical and AI learned answers. Now let's go to the CAE type of simulations we can do. So we saw what the entropy concept for all manufacturing topics. We see that image concept for a lot of default manufacturing, and let's see what we can do for predictive design or optimization. Again, I go back here, and you can see one of the major issues here. This process I just showed, well, we need to do it many times, repeating for parametric studies, repeating it a lot for 100 times probably for optimization, and even thousands of times for reliability, robustness. We need to have mileage on things to know what happens. Now, the issue with machine learning is that the initial, let me put this pointer active. This initial part may be a little bit costly, and what we should really know is that the learning part of most machine learning techniques, apart from a few of them, may be long, but once you have spent this time, well, the rest of it is for free. So instead of going up linearly when you want to do this kind of analysis, well, you can just go flat and have a very good outcome. But this is typically what you want to do for machine. For example, we want to optimize here the front bumper of this vehicle. This is the reference model, and these are a few variants of that model. Now we want to optimize the shape. Without going this page a little bit, I will go to this one. We want to optimize the shape. Here I have defined the shape as variables of the problem, as parameters of the problem, the bumper dimensions on the CAD level, by the way. This is not done on mesh level or anything. I just defined them on the CAD level. Now, my objective is to minimize the pressure and, of course, to limit the lift coefficient to something like that. So I don't want the car to fly up. So here we can see by simply 9 simulations. So again, we are not talking about deep learning or anything which requires thousands of modeling. We are talking about very low number of simulations, and this is really the most important issue when we go into this entropy type concepts and reduced order models. That by learning from very little number of runs, when we can do this simulation and we can find the optimal configuration in a very few short of time. So how does it work? Let me just say a little bit, 2 or 3 pages on how does this reduced order model concept work. Well, you know partial differential equations. Everybody knows how that works. Now the reduced order models, data-driven, they do the inverse of what a partial differential equation does. These are physics-based. So at the basic of the reduced order model, we know the physics, for example, CFD in the previous case, and we know a few responses. We knew a few cases. We know the answer of that physics to a few cases. So instead of going here on the left, solving the differential equation, we go here backward. We look into those previous runs or simulations or even measurements we have, and by associating them to each other, we try to understand what is happening. How do we understand? Well, the concept is more or less simple of reduced order models. Well, you know, nearly all of you know the principle of Fourier transform and decomposition, etc. But this is very much the same. The idea is that instead of looking at a function as it is, a measurement as it is, well, why don't I look at its components as it's once decomposed? Because we can see that these are much simpler functions, which I can formulate simply and predict simply what they are. So instead of predicting a complex phenomena, I just do a little bit of runs. Now you saw in the previous case, I made 9 for the complex CFD Navier-Stokes equation. Here I do a little, something like 6 runs, for example. And based on those, I understand the modes. And then I know that by combining these modes, well, I can get any type of response I want from that particular system. And that's where the physics comes into it. Now, this we know, we call it modal decomposition. It's nothing more than if understanding this blue curve means understanding portions of the response. Here we see I have a peak here, then I have a sort of oscillation here, then I go up again, then etc., etc. Now, if I understand, if I decompose this and rebuild it, I can get any response out of this model. And this has extreme advantages, and we can use then any kind of model with low number of runs. So this is really important. Machine learning does not mean 10,000 runs. This is a false concept. It's only applied to neural networks and its variants. But we have today at our exposure, at our availability, we have the availability of techniques which can use very low number of runs. And these are, as I said, these are algebra. Machine learning is only about algebra. So we can do this. Now, one important issue also I should probably talk about when we go back to this is the sampling. I did mention sampling a couple of times. Well, all sampling are not the same. Here you can see the sampling I have on the left on the same phenomena. Well, does not give me the same information as I have on the right. Here you can see the same phenomena is measured with a lot of outliers here, whereas here it is not. Also, these pictures on the top, when decomposed into what we call principal components, so that once that decomposition technique works, they do not show the same sensitivity. So these are issues which should be handled at the sampling when we do use, close this. Yeah. Now, here you can see that we can use some sort of adaptive sampling by adding points. We can, here you can see that the error in the system error in the measurement can drop. Now, the only issue is that, well, these points cannot be anywhere. They have to be at very particular points. And that this is something which we can do today. I will finalize with a few examples. This time is short, and I think I still have a few more minutes. I suppose someone will shout if I am too long. Now, here I have an example of for automotive structures. Here I have a wheel hitting on a curb, and I can do this, simulate this 20 times. So you see, it's not that much, 20 times. But what I can also do is to add the information from the shape. These are pictures, just pictures which show which one of these 22 tests, which I have here, have been done, which type, how many spokes I had to make the impact. Now you can see that without using the image information, well, I can do some sort of learning and prediction, which is not bad here. But when I do also combine the image and the signal, both two sources of information, well, I get a nearly perfect predictive model. Now, by this, I mean I can just go and use any number of spokes and any impact velocity or any material properties, and I can get the simulation. Same thing I can use for learning again from images. These are I've forgotten the English name. Engrenage, the gear systems, where we actually learn from the images of the contact stress, we learn how the system should be optimized. So we can define parameters here. These are defined here, and we can also make measurements. It's few number of simulations. Or here you can see that if I use a traditional machine learning technique like neural network, etc., I need something like 2,000 runs. So it becomes immediately prohibitive. But if I use the concept which I just mentioned, that means ROM, reduced order modeling, well, I can reduce that to only 24 runs, and then we get the response. Same thing. This is for patients who have stents installed in their veins. So my intention here is to show that, well, it works for CFD as the same way as it works for structures, for acoustics, for gearbox systems, etc. We can use it for multi-physics. That means combining a ROM model with any other physical system. Here I have a CFD model of one of these wind turbines. Here is actually calculated. There's a DOE of one of these which is available. Now, using that and combining it with our CFD code, with any number of these wind turbines can be calculated in real time, and then we can combine it with other physics like temperature, like even movements and so on. So extremely powerful technique, and we can even do layout. I won't go into this picture. It's very crowded and rich, but here you can see on the image on the top here on this image, you can see that actually the flow behind these wind turbines well depends very much on the layout, how you arrange like vehicles, like cars running one after each other. Now, by doing this, we can actually simulate cars running one after each other. We actually do have, I can't show it to you, but believe me, the layouts and arrangements and structural improvements which we can make can be analyzed very, very easily in this way. We can apply it to biomedical.
Yes. Sorry to interrupt your flow.
I'm finished.
Are there many more slides?
No, I can stop now because they're all examples. I can stop in one.
Case, yeah, very good, thank you.
Okay.
So do you want to do a wrap up, or have you got a wrap up slide?
No, I can wrap up on my own. Don't worry, I'll do that. Okay. So essentially, what I want to show you, I'll probably stop with this with this. Yeah, let me go to here. So essentially, what I want to show you is that machine learning is not very data consuming. You can do it with small sets of data. 2, machine learning is horizontal. It can be applied to nearly any technology. 3, it can be used for optimization. And 4, it can be used by many different engineering profiles. So thank you very much, and I'm happy to answer any questions later if there are any.
Yeah, can you hang on, Kambiz, because we're moving into the questioning paneling now. So
I will.
yeah, questions. Yeah.
Yep.
Okay. Thank you. Thank you. No, thank you, Kambiz. Excellent. That was.
We can get all of the speakers into the hot seats now. So we can ask
Hey,
any
it's the hot
questions.
seats. Yeah. There you go. So Sean and Altair.
I hide behind here so nobody can see me.
You know where you are.
Well, very briefly. Sorry, Kambiz, if you can stop sharing. Great,
Yeah.
thank you.
There you go. We can all see you now, Kambiz. We can all see you now.
You can still see me? How can I?
Yeah, we can all see you. Yes.
But I can't see you, so I'm sure.
Ah.
Okay, perfect. Thank you.
There you
Hello,
go.
everyone.
So, I gotta guide this. I really need to get this moving. Because you know you always get to this point and it's like there's a little bit of a who's going to ask the first question. So has anyone got a question? Excellent, thank you. All right.
It's a 3-part question on the quantity of intelligent data that's being generated. All you talked about that. So first of all, how do you see intelligence becoming more of a commodity? So widening individuals' businesses' ability to trade in data and collaborate. Is there a framework for them to do so? So framework of sharing information and collaboration. What's the sustainability of this quantity of storage of intelligence? So, and the carbon footprint, and who is anybody thinking about that, and how we minimise the impact? And information overload. How do we navigate this quantity of information? So, framework for sharing, sustainability, and navigation.
I can have the first crack. I think we're going to have very different takes on this, because obviously Sean is very much on the data management side, and whereas what I talked about was interpolation of that data and creating the neural network. Now, you say volumes of data. I think that's particularly pertinent when you're talking about engineering data, because you've got terabytes and terabytes sometimes from single simulation runs or single wind tunnel results. Now, once you've generated a neural network based on these results, you don't actually need the source data anymore. So you can actually then get rid of that data, and I think there'll be IT managers all over the place. They'll be very, very happy with that, because I've been in those meetings where IT managers are not happy with the fluid themes or the questions for the amount of data they're generating. So you can actually get rid of that data. Now, then you think, okay, but I'm generating new data all the time. What do I do with this? How long do I store it? And the wonderful thing is you can retrain models and you can add data to neural networks all of the time. So you can actually use the new data you're generating, but you don't necessarily have to store it. Now, you made an interesting point about trading data and what's data worth. Well, I'd say, what is a trained AI model worth? And I think that's the real question. So it's not how much is the data worth, it's how much is the interpolation, the usage of that data worth. And I think that's an interesting point. It's going to come more and more to the forefront as models develop. That's my answer. I'll hand over on the panel for.
I'm quite easy sharing, because coming from a racing background, it's more, we don't share it. We're very limited in most race teams are very protective of their data, because it costs us a lot of money to generate. Track testing is not cheap. In terms of sharing, is very limited scale to our customers. Some of it we get forced to share by the governing body who want information on our car for performance management, balance of performance. So the data sharing is not so relevant. In terms of what we do with the quantities of data, part of the work we've been doing is trying to look at generating the correct aggregation functions so that we're not storing all the raw data, but trying to reduce it down to more manageable levels. I mean, we've got years worth of many cars running around circuits, and most of it never gets looked at. But if we can try and generate, as I say, turn it into usable aggregated metricized data, then suddenly you've got a resource. So, but in part of that is it does, you don't need the raw data once you've generated the metrics from it.
Yeah, so lots of questions there, but I think I agree with what the guys have said. From a collaboration perspective, I think there's obviously external and there's internal collaboration. I think we need more of both. Obviously, in some areas it can be quite difficult, but from an internal collaboration perspective, you see a lot of companies creating these center of excellences for data and artificial intelligence. There's a big thing of centralize and democratize. So the center of excellence can centralize all of the different silos of departmental information into one aggregated data lake or data warehouse. From there, then it's much easier for them to democratize access to that to the different departments. And that means you have collaboration because you have a single source of the truth that is good quality information. So the lines of business can then analyze that, and they know that they're not analyzing poor quality information. One of the biggest disadvantages or fear that people have with democratization is if everybody's building machine learning models, they're going to be biased. There's going to be a lot of error in there, but not if there's this collaboration between a center of excellence who can have that single source of truth, that verified information, and from there sort of push to the individual unit. In terms of your data quality or data quantity perspective, I think the guys have covered that quite well. Is you don't need to store everything, and IT people would be quite happy with that. I mean, aggregations and these things is absolutely a valid approach. And to your point about the environmental aspect, I think that's an increasingly important question. And I often think when people talk about artificial intelligence, people jump to neural networks and deep learning and these things that are really energy consuming. There was a report that got for Timney Gebru, who's one of the top researchers in the world. She was sacked from Google where she worked because she released this report whereby it said that a couple of deep learning models can release the same amount of emissions as 5 cars over their lifetime. So a huge amount. Now, of course, not everything needs a deep learning model to be able to analyze. And that's where I think a lot of companies need to be realistic. You know, what is the model? How much information is there? Can we grab a more basic thing like a regression model or a decision tree model? So I think the environmental aspect is huge, and you've seen in the European Union, they released an artificial intelligence act quite recently. So that's going to be a growing conversation. And it does dig in, I guess, to the data quantity perspective as well. I can assure you that Renishaw aren't storing 1.5 terabytes of information every hour. It's a lot of downsampling, aggregating that goes on.
I think I would just add to on the environmental side, the deep learning models, there's several different, huge range of deep learning models. Now, so some of these models done by Google and so on, they're taking weeks and weeks of deep learning on these GPU cluster machines. There's weeks and weeks of it. When you're talking about deep learning for engineering, you're talking a few hours on GPUs, whereas, and are you in theory, and this is the question, that you in theory replacing thousands of CPU hours of computer simulation with some deep learning? So there's a balancing act that we had to do, sure, but I think addressing that, you can address the storage issues of lots of data, which can have a carbon footprint depending on whether your data center is at the bottom of an ocean or not. But also compute. And you just think about the amount of energy compute takes, particularly with energy. bright as in energy generation now. It's finding the right balance, and I think, as we say to all of our customers and everybody we speak to on this, it's finding the right application, the right bottleneck where a AI model is useful. There's no point in applying it to everything. You apply it to where it's useful, where there's a bottleneck, and where it actually make a difference in the business.
I think, you know, having that
Can I,
awareness and awareness of responsibility as a technology it develops, you know, if we're going to learn from other technologies and other processes and industries, you know, starting to think about the environmental impact of what we're developing at the beginning, I think is important. So thank you for being part of.
Kambiz, do you?
yes, can I just say a word on the 4 topics very shortly? Now, on the quantity, I learned some 15 years ago when I was running the Cranfield Impact Center, where motorsport cars were coming in to be crash tested just before the Silverstone race, that there is huge amount of data already available, which people just put it on a CD and never even load the CD. So data has been there, has been always there, I would say even much earlier than we think. It's just that we are exploiting it today. So the availability is not an issue. It's the capability and of course the readiness to use that data, which is today new. And I think this is something important. On the carbon footprint and the issue of the cost, I very much agree with my colleague from Altair. I think the moment you talk about machine learning, people go into their imagination and think that everything has to be deep learned, etc. No, a lot of things can be solved with simple regression. You know, a straight line can solve 50% of machine learning is regression. And the other 50% is different versions of regression, by the way. And to be honest, neural networks is also regression, and everything else is regression. It's just that the way we are doing it today is probably adapted to computers. We are doing it in a more automated way, and we don't need to do all that for physics space. The ROM system, which I just showed you, has the capability because it knows what the physics is behind it. We call this physics-based machine learning. We know what is the physics behind it, and we can use very little number of them. So this is, I would say, an issue which is solved or solvable. About the carbon footprint, I think a lot of things are scandalous today. If we talk about the carbon footprint, including this video conference I'm doing with you. You know, in a few years ago, you didn't need me to tell you these things. You would probably find locally people to tell you the same thing, as we have 3 gentlemen sitting there, all 3 of them younger than me and very handsome looking. But today we do a lot of things in a different way. We call this innovation. So we have to live with it. We just have to reduce. We just have to do it reasonably. And I think with machine learning, at least for engineering, we are very much conservative. We are not, you know, we are not interested in finding patterns in how people buy shoes. We are interested in doing design and less computing, by the way, and less experimental tests. So this is our intention. On the overload, the last word, we are going more and more into cloud-based machine learning. And I think that is one of the reasons, this overload, because of course, huge amounts of data, we can't store them, we can't have them, but there are, I think, solutions coming on the market, which I think will solve this problem.
Oh, yeah, the whole panel response there. I think that really has consumed a lot of time, actually, but a really good, 3 really good questions there. What I've realised is what we've been capturing some of the online questions as we've gone forward as well as some others. But maybe if I just randomly pick a few. The observation is that we are actually going to grab all these questions and give them to the respective speaker, and so you'll be in answer mode a bit later on through online if you can. So, quick question, Andy. It was aimed at you. What type of data do you input to your? Sorry, what type of data do you input to your data? CAD? Question mark. Mesh or images?
That's a great question. Mesh, shape, STL file, whatever that may be, and associated physics in whatever form that may be. So everything from a CSV file to a CGNS file to a NASCAM format, whatever that may be. So we're completely agnostic when it comes to input data.
That sort of follows the statement of the question. I think it was more of a, yeah, it was a question. Are you able to input any arbitrary geometry file?
Yes.
Yes, there you go. So we answered it. Yeah, good one. Another quick question for yourself then. Your models are able to predict only inside of the data domain. Sorry, I'm reading this. Scroll it. Domain. They were trained on. So models were able to predict only on inside of the data domain. They were able to predict on. Are they able to extrapolate outside of this?
If they've seen a window of data that covers that, I mean, you've got to train your engineer. You wouldn't ask a crash engineer to do the aerodynamics of your car, and you've got to take it in a similar way. The model can only do what it's trained on, same as an engineer can only do what they know and they've studied and they've got their experience. Hopefully that answers that question.
Thank you. And then, how are we doing on time? We're a little bit over a minute. I'll make this the last question. Sean, it was over to you. I think it's quite a holistic one. What are the first steps a company should take before testing AI?
Yeah, so it's a big space. So I think you definitely need to set expectations first and foremost. Gartner, who are the big market analysts, they've said that 1 in 5 AI projects are successful at the moment. So not everything is successful, and it's all about trial and error. So I think you certainly, first and foremost, you set those expectations. I think the second thing you need to do is invest in the data and the quality of that information. The age-old saying of garbage in and garbage out, it's always the same. You're not going to get anything if your data is not in good quality format, good centralized format. I think you need to invest in training the internal workforce. There's no point going out and a data scientist has been, I think, the top rated job on Glassdoor for the last 6 years. The reason being is because they make about $150,000 a year. They're really expensive people to come in. So before you go out to the market to try to hire these people, you should look internally to your existing workforce, see if you can see any champions in that, people like Altair here, who wants to succeed with information, is motivated to succeed with information. Get these people in your organization and get them to fly the flag for data analysis. If they can be successful, they will influence others who can be successful. And it's change management. You're not going to influence everybody at the same time. Focus on your runners. After that, focus on your joggers. After that, focus on your walkers. And forget about the laggards for a couple of years, because you just need to focus.
John, can I bring you back to the point you made that's really relevant? Because your point, actually, it's the business case.
Yeah.
Before you start going down any of the technology, you've got to understand what the business outcome is going to be from it. And we've seen so many of these things go awry because they're digital officers' pet project, and it's got nothing to do with the business outcome.
Yeah.
And it has to be. And the first thing we fall into really deeply is, where is it connected to your business? How's it going to transform the business?
Yeah.
Because if it isn't going to transform the business won't fall in behind.
Yeah. The why, not the what.
Yeah, good question. And that
was his answer.
Yeah. Good answer. Yeah, I think there's a couple of questions around that, you know, that really thread into ROI. You know, I think it's quite an important point to probably finish off on. That's good. So I'm very conscious of time. I think we've got to do the wrap up now. So look, thank you everybody for your attendance. Those have been some really great